In this bonus lecture, I'm going to be talking about how to draw a normal probability plot. And what's going to be used of a normal probability plot? It is going to be a graphical, descriptive, statistical method to check whether a population may be normal distributed or not using the sample observations. So that is a topic actually starting from chapter 8, which was lecture 7, which is about the confidence interval calculations, and it's going to continue with the following chapters, which are going to be hypothesis tests. In those chapters, the methods that we are going to be using, especially related to t-distribution and chi-square distribution, are going to be based on the assumption that population is normal distributed. Remember that we may have a question like x is equal to, now these are the observations, 1, 5, 6, 7, 10, let's say. Then we ask, find a 95% confidence interval for population mean here. And in order to continue this question, we are going to compute the we are going to use the t distribution here. Note that we have to assume that x is normally distributed. Or we may ask the question is, again from this sample, find the 95% confidence interval, upper and lower confidence bound sigma square. And for chi-square distribution, it is much more even compared to t distribution for the confidence interval formula. X should be, it's much more important that x should be normal distributed. So the question is, how can we test whether the distribution of the population is normal distributed? Well, there are a couple of more formal tests related with that, but here in this lecture, I'm going to be emphasizing, I'm going to be only talking about the graphical the descriptive statistical procedure, which is normal probability plot. So what is normal probability plot? It's a very simple procedure. We are going to rank order the sample observations. Then we are going to draw the rank order observations with respect to it is cumulative distribution probabilities from normal distribution, and we are going to check whether they lie on a line or not. So let's see what this means. So I have some x values here. This is from an example from your textbook. Actually, these are the battery lives in minutes. And let's say that actually there are 10 observations, 10 specimens here. So this sample size is equal to 10. So n is equal to 10 here. Now, this sample, the question is, we would like to continue with the question and estimate the confidence interval for population mean, so mean battery life and maybe variance of the battery life. But the thing is that we especially would like to know whether, or we'd like to estimate whether the x, the population, the parameter which constructs, from which the population is made up of, whether x is normal distributed or not. If x is normal distributed, then we can apply t distribution and chi-square distribution easily. So one thing that may come into one's mind is to draw a histogram, because actually we have a nice graphical procedure to show the distribution of the sample here. Unfortunately, since we have a sample of only 10 observations here, we would be actually using at most 3 or maybe 4 number of bins. And if you use 3 bins, this is going to be the result that you are going to be obtaining. And as you can see, this has got nothing to do with normal distribution. When it comes to 4, well, one may tend to think that this may be normal distribution, but even dividing this into 4 equal bins may be even too much, because we have only 10 observations. So especially when you have a small sample size such as this one, and note that small sample size is the important case we are considering right now, because if, let's say, sample size are equal to 50, we would not care whether X is normal or not, because X bar will be already normal distributed. So we would be due to central limit theorem, so we can easily use normal distribution. Well, of course, when it comes to the confidence interval for sigma, we would be using chi-square distribution, and in order to use chi-square distribution, still X, whether being normal or not, should be checked. So for n is equal to 50, maybe you can plot a histogram, and this may give you an idea. But still, a histogram will not be very sensitive, or it is not be very reliable in detecting the normality of the distribution, because actually an histogram may show whether a distribution is symmetric or not, but being symmetric does not guarantee being normal, because note that this is also a symmetric distribution, right? Around this median or mode value. These two probabilities, the areas are equal to each other, but this is pretty much non-normal distribution, as you can easily see. So what do we do step by step is this. Actually, it's a very easy procedure, but usually we need a computer to do that. That's why I do not include this in this course. Anyway, so what we do is this. First, we rank order the observations. And rank order these observations from the smallest to the largest is achieved by this very simple command on MATLAB. And the next thing that we do is, once we obtain these values, and note that here x1 is going to be equal to 176, x2 is going to be 183, x10 here is going to be equal to 233. The next thing that we do is actually defining or determining the quantiles here. Okay, let's show the quantiles. Actually, I could have used Q here, but the problem is we have already used Q for quartiles, if you recall, Q1, Q2, Q3. So instead of using Q, I'm going to be using P, like percentile. And the only difference between percentile and a quantile is we multiply a quantile by 100 and we determine the percentile. Anyway, percentile of the ith observation is, quantile of the ith observation is going to be determined by this very simple formulation. This is general for any sample size. We are going to be using this. So for this specific example, the first here, let me write quantile value, corresponding quantile values. This value is going to be the first observation minus 0.5 divided by 10. So this is going to be 0.05. This value is going to be 0.5. This whole value is going to 0.05. The second observation is going to be 0.5 divided by 10, which is going to be equal to 0.50. And if you come at this point for the 10th observation, minus 0.5 divided by 10 is going to be 0.95. Now, the nice thing about this formulation is PI is going to be always between 0 and 1, which is actually a property of course, quantile. So it's going to first we rank order these observations, then find the corresponding quantile values using these values. And on MATLAB, it is straightforward to do this. Actually, if we write P is equal to from 1 to 10 minus 0.5 divided by 10 observations, you find the corresponding quantile value. Now we use these quantile values in this manner. For instance, 0.05 is if we plot the standardized normal distribution curve. 0.05 will correspond to the right-hand side tail area. Actually, it's going to be the cumulative distribution function value here. So this area is going to be equal to 0.05. So what we are trying to find is the corresponding Z value here. So it's going to be basically equal to, using the previous notation we have used, this is going to be equal to Z 0.95, or you can write it that way, minus 0.05. So therefore 0.15 is going to be this point, right, minus 0.15, such that the right hand side tail area, actually this part, is going to be equal to 0.15. And it goes like this until here. We are going to have z at 0.95. Please note that after z at 0.45 minus this value and z as 0.55, then we are going to change the sign here. Z 0.95 is going to correspond to this area here. So basically this is going to be Z 0.05, such that this area is going to be equal to 0.95. So therefore we convert the quantiles to the corresponding standardized normal distribution values. That's that idea. So therefore Zi values, if we call each of these values Zi, this probability cumulative distribution value will be equal to 0.05 value, which is actually equal to 1.66. So actually it's very easy to find this on MATLAB using normal inverse function. You can find, given the cumulative distribution function value, you can find the corresponding value. Actually it's going to be 1.965. With of course a minus sign, which I forgot. And the second value is going to be 0.15, which is going to be, again using MATLAB, this value can be easily found, minus 1.04. So all these values can be directly found using these PI values. So let's first, since we have already have the PI values, let's write them again. It's going to be 10, 1 to 10 minus 0.5 divided by 10. Then what we need to find is normal inverse applied at these values. And these will be equal to minus 1.65, minus 1.28, up to all the values 1.65. So we are going to find the corresponding Z values. Note that during this transformation, we have used the normal distribution assumption. So if these are the quantiles that we have, the corresponding Zi values should be equal to those values under the assumption of normal distribution. On the other hand, these are the actual Xi values. So let's convert these also to standardized. Let's convert these to standard values, and this is going to be, let's call these Z sample. They are going to be equal to X values. Each of the X values, they are going to be subtracted from X bar. If I can write it here, let me write it here. Actually, it's going to be easier. Z sample of ith observation, let's say. That sample I is going to be equal to Xi subtract from X bar and standard deviation of X. So it's going to be this column here, ZSI is going to be equal to, for instance, 177 or 76. And if we find the mean values of X, then it's going to be equal to 196 divided by standard deviation of X. 16.12 or 13. And this is going to be equal to simply X minus, and let's call them Z sample. They are going to be equal to X minus mean X divided by standard deviation of X. So this value is going to be, for instance, minus 1.27. So these values are going to be converted as minus 1.27, minus 0.84, and up to 2.07 here. Note that these Z values are determined from the quantiles, which are actually determined by the rank order Xi values. So the exact Xi value information are not used here. So these are the corresponding probabilities or estimated probabilities, and these are the normalized standard random variable values, which correspond to these cumulative distribution function values. Whereas here X values are directly converted to standardized normal distributed standardized random variables. So if the normal distribution is valid, these values and these values should be close to each other. So what we do is we scatter plot these ZS and Z values. And if they are form a line or close to a line, then we can say that these xi values are taken from a normal distributed population. Therefore, what we simply is going to do here is scatter ZS and Z values. Oh, we haven't calculated the Z values yet, so let's calculate them. They are equal to norm inverse 0.05 to 0.10 to 0.95. All right, now let's plot it. All right, this is what we obtain here. Now, in order to also plot this line that you see here, note that the x's here for Z and ZS should be identical. On the other hand, as you can see, they are not here identical. So let's make them identical. So x limit is going to be, the x values is going to lie between -3, let's say, or the smallest value is what, -2, -2 and 2.5. And y limit is also going to be between those two values. Now we include all the observations, and x and y axes are identical to each other. Now we can plot a line here between the x and y limits, which is going to be an off-diagonal term, as you can see here. And a grid function is also, that's something that I do often to show the finer details. And maybe line style of dashed lines with a more higher width, and maybe using a different color is going to show the whole thing better. Let's see. Okay, let this be red, and let these be, let's say the marker face color is something like this, so that it's going to show the whole thing better. All right. This looks like a nice diagram. So here the X label is going to be the standardized observations, whereas Y label is going to be standard normal random variable values, the Y. So now we can see that these seem to lie on a line. Of course, you need some experience to conclude which of these types of scatter plots they fit the line in the off diagonal or they do not fit. But as you can probably see that this seems to fit that those dashed lines. Therefore, we can say that this sample value seems to be normal distributed for a sample size of 10 observations, and hence we can say that population seems to be normal distributed. At least we can say that population does not seem to be too much non-normal. We say that, just like the idea of related to the idea of not accepting the null hypothesis that we are going to talk about in the next hypothesis testing chapter. Well, actually, we have a nice MATLAB command for all of these. If you directly take the original x values and use norm plot command, you obtain this graph, which is identical to this one, as you can see all the values. Well, the limits are quite possibly not the same, but we can make it. For instance, we can make this minus 1.5. Yes. Now, in this case, they are probably totally identical. Yeah, I guess so. Except one point, yeah, we need to also adjust the y-axis here, except one point here on the y-axis. Well, first of all, x-axis is on the x-axis. We can see the original x values. That's fine. We have standardized it. That's no big deal. You can always change them. But the more important point here, on the y-axis, probability is given. Actually, MATLAB, and that's the way MATLAB uses actually is more informative. These values, these 1.65, 1.05, all these values are not shown, but actually these values, these probability values are shown. And this is more informative, and you can actually easily change this so that it's going to be closer to this representation. If you write here, for instance, set at current axis, y tick, where it's going to tell MATLAB to where the ticks are going to be plotted. So it's going to be from -2 to 0.05 to 2.5 here. And the tick labels are, and it's going to be equal to, we are going to write normal cumulative distribution function -2 to 0.5 and 2.5. I think that would be okay. That's not going to be exactly again the nice graph MATLAB plots, but actually it is similar. Here the most important thing is, as you can see, MATLAB does not use equal spacing here, right? But uses some probability values at certain values. You can do a similar thing here, but as you can see, these are at equal intervals in terms of not probabilities, but in terms of z values. So MATLAB uses a figure which uses a non-equal but more informative scaling. You can also do that, but you can see the resemblance in those two figures. And this is how you can show, or how you can confirm that your population is normal distributed. Only a single comment on MATLAB will be sufficient.